Hello and welcome to Water Quality. In this video, I'm going to go over the derivation for the total alkalinity equation. First of all, we're going to start with listing out our dominant species in water. So the dominant species in most natural waters include calcium, in no particular order here, also magnesium, sodium, and potassium. So those are positive ions or cations. And then on the negative side, I have chloride, nitrate, sulfate, and bicarbonate. So these are our big eight. And then we're going to add in the carbonate minerals. And so the carbonate minerals include carbonic acid, H2CO3 star, bicarbonate, which we already put over here, so I don't want to count it twice, but I'll just kind of make this association. And then carbonate. So these are our carbonate systems. And then we're going to add the water ions, which include hydrogen ion and hydroxide. So looking at this list, we need to answer the question, which species can neutralize hydrogen ion at pH values of natural water, about 5 to 9, 6 to 9, somewhere around there. And so pretty quickly we can see that the only ions that can neutralize a hydrogen ion or react with a hydrogen ion are bicarbonate, carbonate, which can actually react with two hydrogen ions, and hydroxide. So if we think about alkalinity as the acid neutralizing capacity of water, um, then we need to include these three species. And we can write an equation based on that idea. So our alkalinity is equal to the bicarbonate concentration. I'm going to put in carbonate, but I'm going to put in a 2 because it can neutralize two hydrogen ions. And then hydroxide. And I'm also going to put in hydrogen with a minus sign because it's kind of like the opposite of having acid neutralizing capacity because it is acid. So this is an expression for alkalinity just based on the kind of intuitive nature of species that can neutralize hydrogen ions. But we're also going to come up with another way to arrive at the same equation. So moving on, I'm going to develop a charge balance based on the species that we identified previously. And so I'm going to put the positive ions, cations on the left side. So I have hydrogen ion, sodium, in no particular order here, potassium, calcium, and because it's a charge balance, I need to put a 2 in front of the calcium because it has a 2 charge, and then 2 times magnesium, and that's it. Okay, on the negative side, I have hydroxide, chloride, nitrate, sulfate, and then bicarbonate, and then 2 times carbonate. Oops. Okay. Yep, that's it. Now I'm going to reorganize these and I'm going to lump together all of my ions that don't react with hydrogen ions. And I refer to these as conservative ions because they are conserved, because they don't react with hydrogen. They're not part of the weak acid system. So I'm going to put these together. I have sodium, potassium, 2 times calcium, 2 times magnesium. And so these are the conservative cation charges. And then I'm going to put all my conservative anion charges over here. So I have chloride, sulfate, and nitrate. And then on the other side of the equation, I'll write out the carbonate species, which include bicarbonate, 2 times carbonate, hydroxide, and then I'm putting the hydrogen ion over here. Okay, so right away you can see, derived from a charge balance, the alkalinity expression that we came up with before. And then on the other side of the equation, we have our summation of conservative anion charges. And we're going to call these summation CACs, cation charges. And then over here we have the summation of the conservative cation charges, or summation CCC. And an important assumption to note here is that we're considering only one weak acid system, and that's the carbonate system. And that's a pretty good assumption in most natural waters. And some systems, like in anaerobic digesters, you have to consider other weak acid systems, but here we're only including the carbonate system, which is good for rivers and lakes and groundwater in general. Okay, so now we have a couple of different ways of expressing alkalinity, and I'd like to put them all here just so that you have them all in one place. And so we have the first one that we came up with, which is alkalinity is equal to bicarbonate plus 2 times carbonate plus hydroxide minus hydrogen ion. And another way to write this is using our alpha expression. So we can substitute alpha 1 times CtCO3 for bicarbonate and alpha 2 times CtCO3 for carbonate. So I'm going to put those together, and I have alpha 1 plus 2 alpha 2 times CtCO3. So I'm just putting together the carbonate and bicarbonate, and then I leave the hydroxide and hydrogen ion as it is. Now I also have, based on the derivation above, the summation of the CCCs minus the summation of the CACs. So now we know that the alkalinity is also equal to the imbalance in conserved species. Now also from the lab or from the experimental side, and this is based on a mass balance, we have another expression for alkalinity where we go into the lab and we measure the pH and do a titration. And I'm going to put that here too, just for completeness. So alkalinity is also equal to the concentration of the acid times the volume of acid added in order to reach the inflection point or equivalence point, divided by the volume of our sample. So this is when we do a titration. Just before we leave, I want to make one other comment, and that is that the units of alkalinity are equivalents per liter and not moles per liter, and that's because it's based on a charge balance. So these numbers that we see in the equation, these are basically, when we have 2 up here, it's telling us that it's 2 equivalents per mole, and then the concentrations in brackets are in units of moles per liter. So I kind of refer to that as the invisible conversion factor. And what it means is that the alkalinity units are equivalents per liter. Now we can also multiply. So if we have equivalents per liter, we can multiply by 50,000 milligrams of calcium carbonate per equivalent, and that will get us units of milligrams per liter as CaCO3. And that's just one of our units conventions for alkalinity and for hardness and other things. And that is it for the alkalinity system derivation. Thank you.